Okay, we are recording.
Okay. Well, welcome everybody to the RISC-V Bay Area Meetup. I would expect some of you may not be in the Bay Area because of the virtual nature of the event. This is a presentation on Cached Coherent Memory Fabric, which is based on influence on RISC-V. My name is Ted Morena, and I'll be just doing a really quick introductory. Let me just share my screen. I just have a couple of slides. So let me see if I can do that over here. So for those of you who are, you should be able to see my screen. It says RISC-V with these bubbles.
Yes, we can see it.
Okay, great. So RISC-V, for those of you who are not aware, I think a lot of you are familiar with what it is. It's basically an instruction set architecture. It sets the specifications for what you can do to a processor core. It allows you to, really have full control. And the real key here is the openness of the specification. And the other part of the openness or of the specification is that it just basically sets what you need to do. It doesn't actually talk about the implementation or how to do it. So, really that's where the group CHIPS Alliance, where we're going to be talking about Tilelink. Tilelink is actually a bus and interface based off of RISC-V. And we're also going to be talking about how Tilelink has been extended, and that's what yields OmniXtend, and the Intel Tofino switch is what we're using to do demonstrations and proof of concept for this capability. So what's really unique is that this is an architecture that's really been influenced and enabled by RISC-V. So the group that all this work's being done in is called CHIPS Alliance. You can see a number of organizations that are part of the group. The organization develops open source hardware as well as software development tools. And there's a number of work groups that are part of this. And so what we're going to be focusing on is really the interconnect work group. And two particular applications or developments within that is Tilelink as well as OmniXtend. So there's also a chiplet interface called AIB that's part of our interconnect. That's also an Intel supported and sponsored project. So lots of different activities. You can see we have cores work group, and we have software tools work group, and so on. CHIPS Alliance, if you want to know more, you can go to the chipsalliance.org website. The whole idea of the group is it's an open, no barrier collaboration, allows companies to share development resources, lowers the cost of development, and can also provide a Red Hat model. You can introduce something that's open and then monetize it, put support services around it. So that's the end of my presentation. I'm going to stop my share. I do want to let everybody know if you have questions, there is a Q&A box that I'll keep an eye on and monitor. And then you can also, I believe there's like a place for you to raise your hand. So Jeffro, I think, is there anything else that I should say before we hand the baton over to Zvonimir?
No, I don't think so.
I think Wesley is going first, no?
Oh, sorry. Yes, Wesley. I'm sorry. Yeah, so Wesley, why don't you take over? And you should be able to do this.
Looks like Ted is frozen, but Wesley, you can go right ahead. Oh, Ted, you're unfrozen now.
Wesley, are you there? Wes, you're on mute.
He says he cannot unmute.
Oh, okay.
1 second. Give me 1 second to fix that.
Okay. That would be difficult if he cannot talk.
Can you hear me?
So
now we can hear you.
Okay.
How'd that happen?
I don't know. I talked earlier, it worked, but okay, anyway. Let me just share my screen. And all right, here you go. You can see me on the beach as well. Okay. So hi, I'm Wesley. I'm from SiFive. And I was asked to give you guys a brief introduction to what Tilelink is. We use Tilelink internally at SiFive for most of our chip interconnect, where we don't have to interface with other companies, obviously. But I'm going to give you a quick overview of what it is, what it does, how it works, and what the future holds. So, okay, so what is Tilelink? It's a pretty easy one. It's just a protocol for connecting masters like cores with slaves like memory. So that's it in a nutshell. There are a lot of different buses like that. One of the things that makes Tilelink somewhat special is we've gone out of our way to make the protocol have a very simple message vocabulary that works across different levels of complexity. So you can use the same protocol in very simple slave devices, but you can also use it in cache coherent situations where you need to transfer both the data and the ownership of blocks back and forth. So just to walk you through sort of the basics of this, the idea is that you have agents, which are components in your SoC that need to talk to each other, and they can either act as a master or a slave, because the Tilelink protocol, it's a master-slave protocol. It only ever connects two agents together, and you move data across the link that connects them. So an example would be the master might say, I want to do a write. That's a put message. And then the slave, upon receipt of that message, will respond with a access acknowledgement saying whether or not the write succeeded. Of course, you can use the acknowledgements to do ordering of your operations and so on, but that's sort of in the weeds. We're not going to talk too much about. You can also, of course, do gets, access data. So at the simplest level of conformance, you only have to support these two operations. That's it. So if you're writing like a SPI controller or something, it just has to take the reads in, send out the data, take the writes in, write the data, not much more. That's the UL here. So TL obviously is for Tilelink. UL is for, oh man, I forgot. I think, oh yeah, U is for uncached and L is for lightweight. So this is the simplest version, uncached lightweight. And then you have the uncached heavyweight version, which adds atomic operation hints and a few other things that aren't as important. So let's just take a look at what it looks like when you're talking about just the simplest level of Tilelink, where you have uncached transactions, so gets and puts. So in this picture, you've got your agents. These are the bubbles, and they're all connected by edges. Those are the Tilelink edges. Notice in the picture, we always point from the master to the slave. So Tilelink defines what goes on this wire, well, on this interconnect between the master and the slave. To make it just really clear, I've just labeled all of the edges. You can see every agent here acts as a master or a slave on every edge. A single master could be, a single agent could be both a slave on one Tilelink link and a master on a different Tilelink link. Or in the case of like this router here, it could be a slave on two links and a master on two links. So agents are connected to multiple Tilelink links potentially, and they can take on either the master or slave role or both. The Tilelink protocol, again, it's only talking about what happens on these edges that connect the agents. We don't tell you what you have to do inside an agent. That's the microarchitecture, that's up to the designer. So here's just an example. Say the processor wants to do a read, it can issue a get message to its immediate neighbor. So it says from the master, the core is the master, issues the get request to the slave, and then the slave is forced under obligation to answer that get. But he might, send it through the network such that the get message is sent over each of these Tilelink links till it eventually gets to the memory. And then, of course, the memory can respond with the data and the answers come back. So what we've seen here is we generally draw on the pictures master to slave, points from master to slave, but sometimes the messages go in the opposite direction. Right? Okay, so I mean, that's pretty straightforward. I think everyone's familiar with buses like that. There is one thing, though, that you might want to improve. So gets and puts essentially the ownership of the data to the slave. What do I mean by that? I mean, so it's very simple that like if you're a master and you send a request out, first of all, you're only sending it to one person, your slave connection, obviously. But if you're like an interconnect, like that router in the picture here, and you have to decide message came in, where do I send it? It's really simple. You just know where to send it because it's whoever owns that address. That's where it goes. So it's very easy to like route when you're only having gets and puts. And also, it's very easy to resolve any kind of ordering or race conditions, because if you're a slave that's memory, the requests come in, and when they arrive at you, the memory, you decide the order of the operations. So this is a really simple model to work with, and it's pretty decent if you're doing like high throughput, latency insensitive kinds of operations like DMA. So like if you're streaming a lot of write data to or from like a disk or the network, this is a pretty good model. But obviously, I wouldn't be talking if there wasn't something you could do better. The question is, what if the data is far away, perhaps across the chip or even over the network, and you want to use it more than one time? So also that if you're in that situation, those repeated accesses might waste traffic and it might waste power. But particularly for processors, and at SiFive, of course, we sell processors, so we care a lot about this scenario. Processors are quite sensitive to latency. So if you do like a load on a processor and a lot of instructions depend on it, you want to get your answer quite quickly. So that really hurts performance if you can't answer the query without crossing the chip. So that's where we come to transfer of ownership. So Tilelink lets you move where the block is owned. So just a quick terminology thing. A block is just a chunk of memory, typically 64 bytes or 128 or in this range, right? Just a chunk of memory, and that chunk of memory can move throughout the system, like who is responsible. So again, in the simplest scenario we were talking about initially, it's always the slave owns the cache block. So if the master wants to perform operations, he has to send his request to the slave. The slave does whatever the thing was, like get or a put, and it gives the answer back. So that's, in that scenario, the only person with a copy of the block is the slave. That's the unique case, right? Only one agent has it, and it's the slave. You can also, when you have data movement, and ownership movement, you can move that relationship in a cache. So the master can become the person who has the only unique copy, and then he's able to do his reads and writes without having to go across the link. So he's taken the block from the slave, and now he owns that block. And if the slave wants to do an operation, it's not allowed to anymore. It has to ask for the block back from the master. And finally, there's this case where you can have it shared. So both the slave and the master have a copy, and they can both therefore service reads, but neither of them can perform a write until a change in ownership happens such that one of the sides is unique. So that's the way Tilelink ownership operates.
Wesley, just hold on a second. I just wanted to see if you might be able to answer a question that came in on the chat.
Yeah, I was trying to figure out how to work that. And
okay, yeah, I mean, do you want to just answer it live really quick?
Sure.
Go ahead. The question is, are there any restrictions on how quickly the slave needs to respond to a request?
No, the Tilelink protocol explicitly forbids you from, in fact, building timers into the protocol, because we're going to come to this later, but the Tilelink protocol, if you build your system conforming to the requirements of the specification, the system cannot deadlock. So if you have timeouts in a system for slow responding slaves, you can end up in a situation where you answer a message twice. Like you sent the request to a slave, the interconnect decides the slave is down and so responds with like an error, and then later the slave responds with the actual answer. Those are really difficult problems to deal with in a real system. So actually the Tilelink protocol is just like flat out, you're not allowed to put timers in unless you're interfacing with a device that's known to be buggy, and if you do put timers in, you've got to cut that device off completely. So there is no baked into the protocol time limit. In fact, the opposite. But in practice, obviously, the time it takes to respond is going to depend on the memory you're talking to. If it's something on chip, probably 100 nanoseconds to DDR or something. Cache, if you're talking to cache, less than a nanosecond. You're going out to.
Yeah, Wesley, yes, sir. Keep going. We just wanted to get that quick answer.
Sure. Sorry. Yeah, you got me on a side. Anyway, moving on. So how can ownership be exchanged? So we've seen in this picture that the ownership can move from the slave to the master or be shared. So to do that, we need to have messages that can do it. So the operations can be initiated either by the master or by the slave. And the operation might be causing the master to increase his ownership or the slave to increase his ownership. So for this sort of quadrant of four things, there's obviously four possible messages. So the acquire message is a message a master sends to obtain the block. So in this picture, that would be like, you started with the block owned by the slave, the master issues an acquire, and then you end up with the master owning the block. Similarly, you could have a master initiated release. So this is really common in caches where you want to pull something new in, but you don't have space. So you have to get rid of something you already have. So that's where you're like, I have this block, I don't want it anymore. Here, slave, you can have it back again. That's a release message. Another really important one is probes. This is where you have a so an interconnect. So like, for example, this router here, say, and one core takes the block and the other core wants to perform an access. So you ask the router for it. The router has to be able to get it back. So that's the probe. So that you can send a request back to a master and be like, hey, give me that block back. So the slave can recover its ownership. There is actually a fourth potential thing that very few protocols implement. Tilelink also doesn't currently implement this, although there has been talk of potentially adding it. This is the so-called stash. This would be where a slave decides that a master should actually have a block. An example might be like a really smart storage controller that has seen many access patterns, and he knows that if you've read this block and this block, you're going to want that block next, sort of like a reverse prefetcher. And so when he sees the next core ask, he can say like, here, have this block. Anyway, but regardless, these messages here, the acquire, release, and probe, supporting for those, that's what brings you to the third conformance level of Tilelink cached. All right. Okay, so how do you actually build a bus like this? You need to know a bunch of things. You need to know the types of messages that are sent. We've talked about all the important messages in Tilelink now. You need to know the field definitions, things like, you know, the size of the block being transferred, who sent it, what's the address, so on. You can read the spec for that sort of stuff. A really important aspect of any bus protocol, in particular cache coherent bus protocols, is order and what things happen in what order. So like what messages may wait on other messages and what messages must wait on other messages. So in Tilelink, that's dealt with by like, we have 5 priority levels that we define in the spec, and every message has a specified priority, and you're not allowed to wait on a lower priority message to serve as a higher priority one, in a nutshell. And if you follow those rules, then like I said earlier, actually you can prove that a composed system of correctly implemented Tilelink blocks cannot deadlock. There is one last thing you need to define, of course, which is how do you code the messages on the wire. The nice thing about Tilelink is you can serialize it lots of different ways, and in fact, we have done so. So this is the—
Wesley, hold on a quick second.
Yep.
Can you address the question that came in? Is it?
I don't see them.
Okay, yeah. So I'll ask it. If there's multiple masters across the network, what will Tilelink say about memory coherence if masters don't have the same latency? I think that's the question. And that may not be for Tilelink. Maybe that is an OmniXtend question.
So, well, it's this question for both, I think, since OmniXtend is Tilelink on the network. But the answer, okay, so if you have masters with different latency, I mean, that's sort of like a NUMA system, right? So for example, on my desk right now, I've got 4 VCU1 FPGAs that have OmniXtend, and if one of the FPGAs has a cache block and a different one wants it, well, then there's a high latency penalty to go get that block back. So bouncing a cache block between distant masters does take longer, obviously, than bouncing a cache block between masters that are on the same chip. So if you have to move a cache block a long distance, it will take longer. I mean, yeah.
Okay, thanks.
So this picture here is a picture of the on-chip protocol we use in this 1.9 spec, or sorry, 1.8 spec. I can't actually see my own slide. Yeah, 1.8 spec. So in this spec, this is showing like an example get message. I'm not going to go into the details. If you care about this serialization, you can read the spec. Somewhat relevant is you see the priority here on the left, that's letter A and D. So when you're doing just straight normal Tilelink uncached, so TLUL or TLUH, you only need 2 priorities. That's the A and D priority. So here we see like a get message went out, the access act data comes back, another get message goes out, the access act data comes back. Right. So there's different ways you can serialize Tilelink. You can do it on the parallel, with the 1.8 spec specifies a parallel ready valid bus. So that's this one here. This is the one we mostly use internally at SiFive on chip. Some people have done things NOC-like, where they take on chip the Tilelink messages, turn them into packets, and then send them over the NOC. The idea here is just Tilelink is a lot of wires when it's parallel. Like you've got, that's not in this picture, but if you have like an address bus, it's potentially like 40 or more bits wide, and a data bus can be wide. So if you want to save on wires, like you can turn it into a NOC, where it's sort of like a mini serialized protocol on chip. You can also do it off chip. So we have like a packet-based parallel credit bus version that we called ChipLink. That was in a product we shipped, I'm not sure how many years ago now, but quite a while ago. But it's proprietary. And you could also do it over the network. So I refer you to the next talk about that. Here's just a picture of like a real chip that we've taped out. I'm not sure how long ago, quite a while at this point. You can see that it's got like 4 cores here, a bunch of Tilelink switch. There's a cache, DDR controller, a bunch of slaves. There's a chip link thing where you can go over to another chip to prototype like IP you'd like to attach to RISC-V or SiFive chip. This is one of our chips. This is SiFive. Freedom Unleashed 540. So you can see though that the whole thing is glued together by Tilelink edges. So you've got between the cores, the U cores, these are Linux capable cores. These, when they talk to the L2, they're speaking the coherent version of Tilelink on these edges here. And the E core is like a management core. It doesn't have caches. All the iCache doesn't really count, but the iCache isn't kept coherent in RISC-V usually. So this is just the uncached protocol. When you get on the backside of the L2, you're just speaking the uncached version again. When you get up to chip link here, so the cores can actually go and they can cache memory from another chip. So if this had, say, a DDR controller here, you can actually pull that block all the way over here, all the way into the L1 cache of the core. Whoops, of a core. So yeah, that's sort of the idea also of OmniXtend, right? You're going to take remote memory and you can use it in your own local cache. So even though normally to go over here on your first axis, it's like maybe 2 microseconds. When you're using it normally here, you're back into the, low nanoseconds access time. But yeah, that's it. All those, and all these peripherals here, they're all speaking the TLUL protocol because why would you do more? These are easy peripherals, just speak the simplest protocol. So in summary, Tilelink defines a single message vocabulary. I didn't mention this earlier. I meant to, but I got derailed. This is really helpful for interoperability because you can just take like these different components that we've got with the different conformance levels of Tilelink and just plug them together and it works. I don't know if any of you have worked with like AMBA protocols, but things like AXI, AHB, ACE, CHI, they all have different semantics. Like the messages are different, the protocol fields are different, the ordering rules are different. And so you end up with this really expensive conversion whenever you want to go from one protocol to another. So the nice thing about using Tilelink is it's one protocol. It just has sort of levels of conformance. When you go between those levels, the semantics don't change. So the order semantics are the same. The rules for what messages are responded with, what messages don't change. You don't have to worry too much about the impedance mismatch of the protocols. And because we have the 3 conformance levels, you only have to pay for what you need. So like here we had all these tiny peripherals. They could just use a simple protocol and not pay a lot of hardware because there are a lot of them. But here on the cores, we want to pay the hardware for caching, so we do. Finally, because there's this singular vocabulary, it doesn't mean there's only one way to transmit it. And so that's where we have different ways of serializing, like we were talking about. You can do it parallel, like a parallel bus with the address and data in parallel. You can packetize it. You can manage the transmission of your messages ready valid or credit based, either on chip or off chip. So that's it.
Wesley, one more question. Does Tilelink-C support burst serialization for grant data messages?
Burst serial, yes. Grant data messages are almost always bursts, so yes. Or you're asking, maybe this question was directed about OmniXtend, in which case the answer is still yes. All messages sent over OmniXtend are sent in packet form, so your header comes first and then the data payload.
And then we had one other question. Let's see, do the agent nodes perform a handshake to decide which variant of the protocol to use?
No, so on chip, you know this ahead of time. If you're going to do that would be a waste of hardware. So generally you hook up agents that conform correctly. So at SiFive, we have another technology which I have not talked about, diplomacy, which does this sort of handshake at compile time so that you only put down hardware that you actually need. But there's no handshake once the chip is like built. That would be a total waste. Like you can imagine if you had all these little slaves and they had to like negotiate before they could turn on. That would
say Wes, this is Dan. Can you guys hear me?
Yes.
Yeah. So this was probably a question relating to also to OmniXtend, right? So in case of OmniXtend, it's a different situation. Because,
sure.
Yeah. So can you touch on that?
Okay, sure. So I was trying to answer the Tilelink question. I thought it was Tilelink, but yes, if it's OmniXtend and you're plugging together chips that don't know about each other, then yes, there is, we're working on, I don't know if the official name is still Screech, but at one point it was called the Screech protocol. The idea there is that when you plug two chips together over OmniXtend, they broadcast their capabilities with essentially device tree, and then a coordinator node assembles the aggregate system and then tells everyone the answer. So that's how discovery works when you are actually hot plugging hardware. Again, in a chip though, that's very different. There's no hot plug in a chip, so you wouldn't want to pay that cost.
Right. And then the last question, which I think may be an OmniXtend question as well, but the picture you showed of the Freedom Unleashed had 4 cores. Can it be 16 or more
I mean, Tilelink doesn't
for
have
cache coherence?
Right. So the Tilelink protocol just tells you like what message you send back and forth. It doesn't have any, I mean, it doesn't say anything about a microarchitecture. If the question is how many cores can you build, that's more a question of microarchitecture. So you'll notice in this picture, we have a switch. What's not said in this picture is the bank here. The bank L2 has 4 banks. And if you have a switch, which is a crossbar from 4 to 4, the cost of a switch grows up quadratically. So this particular microarchitecture probably would not scale too well if you put 16 cores down right here. On the other hand, we would never build a system that way. We'd probably stamp out this whole gray box 4 times and then connect them with like an L3 or another level of some kind of coherence management there. So the Tilelink protocol says nothing about the limits. It's all about what your microarchitecture is. I don't think this microarchitecture scales up to 16 cores in the gray box, but you could stamp out 4 of the gray boxes, no problem. You could build a ring topology instead of a crossbar that connect the things together. So, I mean, it's really scalability questions are microarchitecture questions. The Tilelink protocol stays the same regardless.
Okay, why don't we, let's move on. So Zvonimir and Dan, why don't you guys take over the screen? And Wesley, maybe you can look at the question and see if you can type an answer. So we need to keep going here.
Okay, I'll try and figure that out.
Okay. So Zvonimir, are you going to share?
Having some difficulty coming off of mute.
Am I sharing?
Yes, we can see it now.
All right, excellent. All right, so good evening, everybody. Thank you so much for coming to this meetup. I'm excited to talk about the OmniXtend fabric. 20 minutes probably not enough, but we'll kind of try to, Dan and I will try to cover interesting things, how this actually came about, and then we'll share some exciting experimental results, data and measurements we've done on the OmniXtend implementations. So I'll start with the data center CPU vision and recently announced backplane reference design. And then we'll jump into details of our architecture and implementation and some performance measurements. So the vision of a data center of the future is a obviously multi-threaded, multi-core CPU. We see importance of getting to out-of-order RISC-V cores that can support general purpose operating system and software applications. But we believe that most important connectivity for the CPU systems are those related to memory and accelerators. And this is basically how OmniXtend came out to be. We wanted to develop open source interface, open source implementation of the interfaces that can be used to bring memory and large amounts of persistent memory to the system. That was kind of the primary motivation. Along the way, we obviously discovered how interesting it is to actually bring cache coherent cores into the system that can be used for specialized workloads, important machine learning and inference, and allows those subsystems to share memory coherently with the main cores that are running the OS. So that's really how this kind of came to life many years ago. And the vision is really to allow then a large number of RISC-V compute nodes to connect to universally shared memory, exactly like on this picture. We very much like the vision of using programmable switches. The base version of the protocol will work with Ethernet switches as well, as it's on top of L2. Programmable switches allow to do interesting things, potentially bring more performance in the system. And this kind of architecture enables memory appliances. So for those of you who have heard about aggregation and disaggregations with storage, where you can virtually move storage and associate it with a specific node, or pool the storage from multiple nodes to present shared storage. This is exactly kind of things that we envision possible with OmniXtend. And we are interested in building memory appliances for this kind of system. And obviously, we are also very interested in the RISC-V coherent nodes that can offload AI workloads. And one amazing, interesting thing here, we are in the early days where we are hooking up Western Digital and SiFive hardware. But everything about the standard is in open source, and a lot of implementation pieces are also available. For example, Tilelink implementation is available and can be obtained at the CHIPS Alliance GitHub. So this in principle mean that multiple different vendors will be able to use OmniXtend, and that people and marketing managers will be able to envision cache coherent systems with equipment for different vendors that can share memory. And this is a amazing board. It took us a while to design this. Our former CTO Martin Fink unveiled this board at the in the presentation on the RISC-V summit last year, and we are bringing this board up in the lab. It's not fully brought up yet. Corona got us kind of slowed down, as the total setup with oscilloscopes and the ESD production for the board kind of has almost 100 kilos, so it wasn't exactly portable. But we are working on it, and when we got at least few of the QSFP lanes and small form factor lanes up and running, we'll share the designs with the whole world. I think currently the designs are available to CHIPS Alliance members in the private folders, and we plan to share the board as well. So now I want to jump into I want to let Dan explain a little bit of a background on OmniXtend and show our demo and performance results. Dan, I hope you are unmuted and that
I can try talking. Is my audio good?
Yes, perfect.
Yeah, okay. I'm not running video because my audio is choppy from time to time, so I don't want to make it worse. All right, so hello everyone. This is a slide that sort of shows a very high level vision of what OmniXtend and Tilelink mean. And I imagine that on this forum, most of you know this stuff. But just to make sure, right, if there are any folks who are not familiar with what a coherence protocol means, this is sort of the coming from the direction of memory-centric systems, right? Building systems with large amounts of disaggregated memory. When you ask a random person on the street how to build a system with, a petabyte of main memory, they'll typically draw you something like the first picture on top. I'm not sure if I can point on Zoom. I don't think I can point, so I'll just describe where the pictures are. So the top picture with the DRAM and a DMA engine is typically how folks build systems with large amounts of memory that can be accessed from more than, say, 16 cores or whatever the largest core count today is. And this is a system where you have an RDMA setup. So you have a NIC with a DMA engine, and then that NIC has some software that runs it and sets up some tables that translate your local vision of virtual memory to a remote, vision of a cloud address space. And then you call these software functions to fetch chunks of memory that are typically in the kilobyte or megabyte sizes. Right? That's this little lightning bolt that you see. So this has issues, and the main issue for us as a storage maker is that for certain kinds of new byte addressable storage that has very low latency, the whole process of fetching and context switching and so on takes too long, right? It takes on the order of several microseconds, and we have technologies that are in a sub-microsecond range, so we need something faster. Now, a lot of you might have heard about things such as Gen Z, and that's the picture on the right, where you do away with the DMA engine and you have some sort of tables that translate your local address space to the cloud addressing, but you still have some software that manages this, right? And in case of Gen Z, this was called the librarian. and there are other solutions out there. So this is, again, not what we mean by OmniXtend and Tilelink. So the picture on the bottom is correct, right? The picture on the bottom means that you have a unified coherent space, right? So all your CPUs and all your memory controllers sit on the other side of some imaginary fabric. And your page tables, so that's what the diagram shows. Your page tables may not be local to your SoC, right? That's sort of the key thing here. So if you move on to the next slide. I'm not, oh, it's coming slowly. It's coming very slowly. I think we can skip this one. How much time do we have?
Yeah, we have about 10 minutes. So I think the audience will probably get most excited if you maybe start from the data plane implementation slide, unless you want one of the two earlier ones.
Sure. Yeah. So let's talk about this, right? So can you maximize?
You want data plane implementation?
Yeah, that one.
I think
correct.
this is so that you basically
right.
take it to the demo and
yeah.
show the microsecond.
Okay, so before we jump into the details, right? So this is the actual bit format of the packet packing that we have, and I believe this is already obsolete because I think we've changed back to L2 framing. But the point here is that we've looked at quite a number. So there was one question, right? How do we choose Tilelink, right? So we didn't really choose Tilelink. The problem was there was nothing else out there. And a similar problem that we had with scaling Tilelink off chip is that there was really nothing out there that was open and not proprietary. And also that would be widely available without everybody having to make SoCs, right? And so essentially we converged on Ethernet, and the reason being that that's pretty much the only fabric out there that's completely open, unencumbered, and it's really widely available. It does have some quirks, right? There's no in-order delivery, and it's not a reliable fabric, but we can work around these things. And then essentially what we do is we just package these Tilelink messages into L2 frames, and we call that OmniXtend, right? So when somebody asks you, what is OmniXtend? It's essentially Tilelink over Ethernet. Now, to preempt one of the questions that's certainly going to get asked, is this Ethernet specific? By no means, right? So this is Tilelink over anything is possible, which shows Ethernet just because you can use it without having to jump through too many hoops. So this slide shows, I think this is the obsolete 0.1 version of the header. So the new header is actually available on GitHub. You can download the specification document and look up the fields. And if you happen to be using one of the smart switches, the P4 switch from Barefoot Networks, now Intel, you can actually parse these Tilelink packets in the switch and you can do interesting things to them. So that was one of the great appeals of this method, is that we could actually process coherence protocol in the switch on the fly. Okay, can we move on to perhaps the performance slide? Yeah, this was an example of P4 that flashed by. So this is an example setup that we have in the lab. We probably don't want to describe. Yes, let's talk about performance. So this slide here shows our measurements. By the way, you can reproduce this yourself. All you need to do is you need to buy 2 Xilinx eval boards, and this is a Xilinx VC118 board that runs the SiFive. I believe this was U54, and now it's U74 cores. So the binaries are available from GitHub for download. And what you can do is you can set this up in 3 different ways, right? So you can set it up as a single board, so that's the red line on this plot. Or you can hook up 2 boards back to back with an Ethernet cable. Those are the 2 green lines. And then you can go through a switch, right? So you can basically connect 2 boards to a Ethernet switch. Just any off-the-shelf switch works, or you can use Barefoot Tofino, like in this plot. And these measurements are a little bit out of date because we're still running at 50 megahertz on the FPGA cores. But essentially what they show is on the x-axis is a random memory access test, and the x-axis shows the size of the window within which we're touching 64 byte cache lines. And then the y-axes are latency measured in milliseconds and measured in clock cycles. Again, the milliseconds look pretty bad, but keep in mind that we're running on FPGA at 50 megahertz. So what you see is on the left, right, the L1 means that every test that you access within a 32K window pretty much hits the L1 cache, right? So you only see 2 clock cycle L1 latency. And then as you transition to a larger window up to 1 megabyte, you slowly start to hit L2 cache more and more. So you see about, I believe, 27 clock cycle latency for, oh, sorry, 22 clock cycle latency for L2. And then beyond 1 megabyte, you start hitting DRAM. And so now things get interesting, right? So the red line shows the latency to access local DRAM on the SoC on which the CPU core is. The green lines show access to both local and remote DRAM, meaning that DRAM on the other board, right, through an Ethernet cable via OmniXtend protocol. And you see that these lines are quite close. The reason being that you're not getting the red line here for the local DRAM is that every coherence request has to go across and check that the other cache doesn't have it. And this was an early version of this protocol where we didn't have directory implementation. So essentially all requests had to check all the caches, and obviously this is not good for scaling. So pretty soon we'll have a directory enabled implementation that's going to eliminate this checking of all caches. And then as you move to the blue lines, these are the same latencies when you go through the switch. So you see that the switch adds about 1.2 microseconds to a round trip checking, whether for local or remote DRAM access. And the important point on this plot is that the red line and the green lines, right? So the access is to local DRAM and the access is over a cable to a board directly attached will scale as clock frequency to a large extent, right? Whereas the green to blue difference will not. So this is the actual hard latency going through a switch over the wire and serializing, deserializing at least 4 times and so on. So I think that's all we should say about this plot. And we're probably running out of time. We're close.
I think we can show the
You have a couple more minutes still.
static,
so this is
static demo.
yeah, you can take over the static demo if you want to.
Yeah, so we showed this on RISC-V summit in the booth last year. We had 2 boards, 2 Xilinx boards with bit streams that Wesley prepared, and we had 4 RISC-V hearts running on each of the boards. Heart is a lingo, RISC-V lingo for a thread, or so basically we have 4 cores, and they're 1, 2, 3, and 4. They're all 64-bit Rocket Core U54. And then we have a second node with cores 9, 10, 11, and 12 running on another node. And when we actually go into the CPU info, we see 8 cores. 4 cores local to one node and 4 cores from the other node connected to a switch. So this is kind of very cool. It was a sort of a first demonstration of the open source symmetric multiprocessing protocol or cache coherence. And it's something that Dan and I have been seeking, for many years, and it's becoming a reality with OmniXtend. And I think that's the last slide. I tried to.
So before
I was going into the chat window and trying to answer. I see.
Yeah, I was gonna.
I'm typing up an answer to one of the questions of how much these switches cost. So I can just say the numbers are around 9,000 for 32 ports and 70K for 64 ports. But these switches, programmable or non-programmable, the price is about the same. So they're not I don't know what expensive means to the person who asked the question, but these are not outrageous prices, right? This is all fairly reasonable for data center equipment.
Yeah, I think the other point is, before we hand it off to Curt, we should also just let people know sort of the status, right? Like, you may want to just sort of reiterate and summarize for folks.
Yeah, I just want to add that the cache coherence switches built as a custom device cost tremendous amount of millions of dollars. Ethernet switches are not cheap. It's not something that typically you put into your house, but are normal IT equipment that's fairly normal for any university, academic group, company, etc. So they're not prohibitively expensive.
Okay. I think the questions have been answered, but obviously if folks have some other feedback or questions, I also typed a couple of web links in the Q&A. So if people want more information on OmniXtend, there's a link to the GitHub for like a lot of the details, the spec and so on that Dehan had mentioned. And then also just for videos and sort of more instructional things, there's a Western Digital link. So let's turn it over to Curt.
Howdy, howdy.
Do I have to do something special or Curt can just grab, stop share. All right.
Let's see what we got here. Let's share, try this. Can you see me? See my screen?
Yep.
Yes.
Yes.
All right, now then I go put it in presentation mode and everything explodes, yeah. No, you can still see it, right? Oh, I should move my
Yes, it's still okay.
visual. Great, all right. So we'll dive right in. Actually, I don't have much to say because it seems like the presentation was given earlier. I'm only joking, but I was very pleased to see that discussion of how a Tofino was able to be adapted to all these things. I kind of knew that before, but it was even adapted to multiple versions. So this picture here is meant to show how like classic network elements work. The network elements are essentially fixed function. That's the classic fixed function ASIC. And you don't get to decide how you want things to work. The fixed function ASIC kind of tells you how that's going to work. You can't push down the network requirements into the ASIC. Moving on to the goal in the Tofino case, in the programmable network case, I should say P4 was invented about 10 minutes before Tofino. There was this pent-up demand for something better, and as soon as P4 arrived, it seemed like there was a surge, and Barefoot was founded back in 2013 or 2012 or whatever it was. I'm at Barefoot, but I wasn't there that early. I was in the neighborhood when it was founded, though, and I remember all the energy. So the point here is that we got to figure out what we want the network to do, and that will in turn allow us to specify in our P4 programmable chip the behavior that we want down in that chip. Now the Tofino chip, as I build this out, it's barely Ethernet aware, as was actually described a little bit ago, that Ethernet is the sort of least constrained, widely available protocol, and we get all kind of great SerDes and other devices that have lots of people out there competing to provide those to you. In the Tofino chip itself, there are MAC cores, and I'll show you that in a minute, but essentially we define what we want and we go push down into the Tofino what the behavior is that we want. And other than, CRCs at the end of packets, and it's hard to get too far below 64 bytes, it's not very even Ethernet aware, despite having Ethernet max. We tend not to use too much of the Ethernet specifics, but they're sort of a limit at some level, because now you get down into, there's even physical layer stuff that's effectively Ethernet specified now. All right, so how do we do this? Here's the complicated version, right? You take P4, you stick it through a compiler, and it generates a binary that is loaded into.
Curt,
yes.
real quick. So there was just a question, what does P4 stand for? I know it's a programming language. Maybe you can just quickly answer.
Oh yeah, sure. That seems like a good place to start. It stands for Protocol Independent Packet Processing Programs, or Programmable Protocol Independent Packet Processing. I forget, it comes from the 4 Ps, and I tend to rearrange them sometimes, but it is a protocol that was conceived quite some time ago, and the idea is that we have this is the fixed function version, so sort of classic Ethernet switch that I designed years ago, long before Barefoot, and you have a fixed parser. It does fixed lookups in a fixed sequence. So first we look up sort of MAC addresses, and we decide if it's valid, Ethernet, and then we look up IP addresses, and maybe we look up TCP ports, we look up ACLs, and we do various things. Maybe we even do tunneling, but all of that stuff was just basically hardwired, and you wouldn't have been able, well, I don't know how you could take that and do OmniXtend on a chip like that. On the programmable switch, though, we have the ability. It's a flexible parser. You actually defined how you want to parse things in P4. You compile that and configure the switch by, well, you don't get to see the details, and you don't want to. The compiler does mappings on these shared memories and flexible lookups, and the actions are also pretty flexible. I'll show some of the creative things that people have done with Tofino in a little bit. And there's a variable number of stages. I mean, the chip has limits, 12 for the first chip and 20 for the second chip that's just coming online and be in production later this year. But the program may not use all those stages, which can reduce your latency. And there's various ways it can reassign memories and so on. So all that's very programmable, how fields are assigned and so on. We go through this pass on ingress, and then it essentially buffers up the result, queues it up for transmission, and there's another egress side processing opportunity. It's not required, so in some cases you can bypass egress for lower latency if there's no manipulation of the packet that's required. So this leaves you with a customer definable switch. We say customer from our perspective, firms like Cisco and Arista are customers. Whether they decide to share that on to the end customer is up to them. Sometimes both are possible, that they do their own definition, and then if you pay the licensing fee for the tools, then you can, the end user, the operator, the network operator can also make changes. This is hugely valuable, independent of OmniXtend, but obviously OmniXtend takes it kind of to a new level, because it's really doing creative things down here, where you can define in relatively few numbers of tables how to do simple forwarding, not based on traditional addressing or routing schemes, but you also have the ability to extend that. And as mentioned, you could use even some of the memory internally to the Tofino as shared memory for other devices that are connected to your switch or to your larger network. I mentioned, let's see, what's another good thing to say about P4 here? There are a number of extensions. There are ways that we can create what are called externs to do things that are kind of beyond what P4 does. Things like bloom filters and other kind of creative things. I don't know how applicable those might be to OmniXtend, but I want to give you the idea that you could do something that could potentially combine OmniXtend with other features in your environment. Here's the simple picture again. So it goes through the programmable parser. The parser breaks things up into these sort of header fields that are then looked up in the tables. And then manipulations are done through this match action table, and it's passed on to the next stage. And we've shown here that the header fields have changed between stage 1 and stage 2 because of that manipulation, and so on and so on. It goes through. There's only 4 stages shown here, but there's 12 or in the first gen and 20 in the second gen. And this is just in egress, or in ingress or egress as well. And then they're put into a queue and sent, or put into a SerDes and sent if it's on the egress side. So the programmable parser, as we talked about already, it carves up those headers. We typically, most of our users really are doing Ethernet and typically IP on top of Ethernet. But sometimes once you get past IP, then they start doing more creative things. You could do MPLS, which I suppose is actually in the layer between Ethernet and IP, for example. So all these match action fields are quite generic. There's nothing particularly special about them. And you can combine, make very wide keys, and the memories in here allow for exact matching, longest prefetch matching, and hashing as well. So for large keys, that's obviously useful because can't do a direct lookup with a 64-bit key or a 128-bit key. Let's see. We talked about exact match, TCAM, ternary match for those wide keys where we don't care some bits, 12 to 20 hardware stages. Does this build out? No, sorry. So this is, we showed the n-tuple hash there. We can have drop status. There's other like internal information that we can pass around. So for example, the queuing state in the traffic manager is available and can be captured and shared. We can respond to certain events like packet arrivals, but also time, although we heard earlier that timeouts are not appropriate for, well, at least Tilelink, maybe for OmniXtend. I'm still learning the differences between what works and what doesn't. But we can generate telemetry essentially in a variety of cases. We can do mirroring and so on, which is useful for obviously monitoring what's going on in your network. And potentially that would be relevant for an OmniXtend environment where we would send messages over maybe a traditional Ethernet link to some other device based on what's going on inside the OmniXtend sort of universe. Those telemetry messages are fully in the data path, so the control plane does not need to be involved, which is good because you can tend to overwhelm your control plane. It's not good for the control plane and it's not good for the telemetry, and so they can get sent off to something that's got more horsepower and can gather all that up and then do basically draw the insights from the data as it arrives. Here's some examples of creative applications that people have done with Tofino. So SwitchML, that's machine learning done in the switch. Well, leveraging the capabilities of the switch. If you're into machine learning training, especially, often the training data is so huge, you may be doing parallel parameter regression and multiple servers, and they need to make their contributions all to each other. In the classic model, that's an n-squared kind of a problem. But by moving the parameter aggregation of these updates into the network, effectively in the Tofino, then that n-squared problem turns to an order n problem. And there are actually like several percentage improvements. There's a secondary benefit as well by when something's n-squared, and it's interesting, it seemed like there was a parallel to the OmniXtend discussion earlier, that things scale a lot better when things are order n than order n squared. So typically the cluster size for SwitchML or for large training clusters often maxes out around 16, so you tend to make each of the servers as large as you can. Sometimes you can get it to 32 or 64, but when you have an order n behavior, then you can scale that out to a much larger number without as much pain. And as we've seen, the databases, the data structures that are data lakes that people are crunching on are getting huge, and they want to use as big a cluster as they can to get things to iterate quickly. So that's a quite creative use case. Advanced congestion control. It does seem like RDMA was a part of this discussion as well. One of our end customers actually did some creative work. I mentioned the telemetry, which is INT. Well, they did a variation on telemetry. Telemetry usually goes to some external observer. In this case, they were using some of that telemetry capabilities to actually enhance the protocol, improve the performance of Rocky by either sending ahead to the receiver information that would otherwise come later due to prioritization, or sends back to the sender sort of an early response. There's different variations of this that are being experimented with, particularly around the Rocky protocol. Very much improved latency behavior, particularly on the endpoints. And as a result, you're much more sensitive to the latency in the network, which is certainly very competitive on the Tofino, but the ability to generate this advanced congestion control messages essentially programmatically without respinning silicon. That's pretty much a Tofino capability. And if you want to look that up, that's an HPCC, is the high precision congestion control paper. You can look up SwitchML as well. And then one of the other interesting ones is the telemetry I've already mentioned before. That's another protocol that's been in develop. P4.org developed it early. There's a IOAM group now at IETF that's working on that. The point I'm trying to make there is that telemetry is, there's lots of interest in it, and it's slightly evolving, and having a programmable device is very useful in this case. We haven't talked about, to my knowledge, in that telemetry group, they're not talking yet about OmniXtend, and maybe they should, and having a very programmable device lends itself to that, so that we could do telemetry, take OmniXtend and then send telemetry message out some different port over a Ethernet IP network, as I mentioned before. So that was P4 and Tofino in a nutshell. Are there any other questions, or any first questions? Things I should have covered and didn't?
There are questions showing up on chat.
Yeah, let's see. There's a question in the chat. So I'm not sure. Can you see that?
I can't
Curt,
at the moment. Let's see. I see.
Let me ask it. I'll just ask it. Has anybody gotten P4 to scale up to 100G for classification on FPGAs without eating up the entire FPGA real estate?
Well, that would be on the FPGA side. I could probably get back to you on that by talking to the FPGA group at Intel. 100G, I think so. I know they've done 80G, so then that was some time ago. So I would think that they're able to do 100G on an FPGA with P4.
Okay. So we have a few more minutes here. People want to ask questions. You can certainly ask it in the Q&A or in the chat. Zvonimir, did you have any sort of like next steps or closing, or did you just want to verbalize something? I wasn't sure if you had sort of closing slides.
I
Okay.
don't have a specific closing slide, but I would like to, actually I may even.
So Z, before you go on, there's
Uh-huh.
a question. Can you see the question in the Q&A? How was the Tofino P4 used or modified in the lab by Dan and Zvonimir?
So I can probably take that one.
Yeah, Dan answer, yeah.
Just to be clear, it was used nor modified by neither Dan or I. This was some very bright people, Tudang, Majan, Radi, who work in my group. But yeah, we have not actually modified the switch, right? So the switch itself does not come with any kind of programming, right? It's not Ethernet specific. Like it'll receive Ethernet frame packets, but it doesn't contain, TCP or IP or any of that firmware on it. So all we did was we programmed the switch to accept a specific packet format that's completely different from Ethernet. So all the changes that we did were in basically programming the chip itself. And then there's a different project which Zvonimir showed. So we took the Tofino chip and just made a backboard, a motherboard, that instead of having front plate QSFP ports has different kinds of connection formats, right? Like this new SFFTA 1002 that's going to be PCI Gen 5, and exposes that on the board just as a test for different kind of short reach connections. Does that answer the question? He says,
yeah, I think
the person who has asked is muted, so I don't think.
Yeah, so there's another person who wants to answer the question live. I'm not sure how to unmute them.
Yeah, no. He said it answers the question, and I think the other thing I would add is I believe the P4 code that you get is available on GitHub.
Correct. Well, the code is very minimal at this point because we only have the forwarding code and the control plane setup, right? What we are really, the most exciting thing would be to have the code that actually stops these packets, the coherence messages, and then acts as a directory. So the switch would act as a directory for coherence, because this would allow you to scale out way beyond 4 sockets or 8 sockets that you can do today. So with one switch, you can scale to 256 lanes if you do 1 lane per. But we have much higher ambitions, right? We have ambitions to tens of thousands of nodes. So for this, we would need actually much smarter P4 programming to limit the spread of coherence messages so we can scale better.
Okay.
There was one
just
in the chat.
I also want to clarify, the point was made that when you get the switch, it doesn't have any of the Ethernet IP kind of, it depends where you buy your switch. If you buy your switch, the white box, then as mentioned, it's a raw machine. And if you buy it from, say, Arista or Cisco or something, they set a bunch of P4 in there for you. So you kind of have your choice. But yeah, the good news is if you want your own sandbox, it comes as a sandbox if you get the right from the right source.
Yeah, there's another question. C. Lee had asked, how does a switch OS compare with software-defined network?
So talking about it from the switch side, so if you buy, as I mentioned, if you buy from Cisco or Arista, I think that sometimes they'll say that they'll let you support Sonic, and my guess is that's a negotiation. Typically, Sonic is, oh, I forget what the acronym is now. So they're sort of like asking me about P4, but it's one of the open networking protocols that is very SDN friendly. And then there's also Stratum that is even more SDN friendly. Both of those are available versions of that are available that run on white box Tofino switches. Now, then of course the SDN controller is kind of your assignment, or that's outside of the box. But yeah, Tofino was Barefoot and Tofino were essentially born in the SDN heyday, the early SDN heyday. So they're very SDN friendly.
Also, just to let everybody know, I put in the chat box one more time the link for all these presentations. So let me sort of throw it over to Zvonimir. I think you had something you were going to summarize.
I would like, I don't know if I can share again. All right, I can.
You should be able to.
All right, so I want to show this slide. So these are the active, these are the currently, and oh, it's difficult. A little bit of Zoom problems. So these are the current work groups active in CHIPS Alliance, and the activities that we discussed today, which is a Tilelink protocol standardization, the OmniXtend, which is Tilelink over Ethernet, and also AIB specification for chiplets are discussed in the interconnect workgroup. So I want to encourage individuals who are interested to visit CHIPS Alliance GitHub, and all these activities are open source activities, so we encourage people to participate. And our GitHub ID is simple, just CHIPS Alliance. And in addition to that, companies can join as members of CHIPS Alliance and reach many more resources and collaboration, as well as a face-to-face, well, now not anymore face-to-face, but certainly online meetings every 2 weeks on the development of specifications.
Great. All right, so Wesley or Curt, did you guys have anything else you wanted to sort of summarize or chime in on here?
A good mention of the open source. I don't have a slide related to it, but P4, there's a lot of P4 on GitHub, and there's a lot of openness in that community as well. Just recently, when the acquisition of Barefoot by Intel has sort of supported additional openness. I think there were some things that Barefoot, so I joined Barefoot just after the Intel acquisition. And what I know about Barefoot before then is what I've heard from others, that they kept some stuff a little bit closed, what they felt for their own protection. They don't feel that sensitive to that now, and so they're opening up even more. And there is a big open source community around P4 running on a Tofino.
Great. Okay, so Wesley, or let's see, maybe we'll just hang here for another minute. Let's see. Well, there is another question. Speaking of development in the open, why are there just a couple of commits in the Tilelink repo? There's a discussion.
Oh, good. I can answer that.
Go ahead.
I didn't even know this.
Yeah, so Tilelink has just recently been moved from the previous repo, so it's relatively new to the CHIPS Alliance, but it's been around for super long time, obviously more than 5 years.
Okay. There's also another question. Tilelink looks nice, but only used for RISC-V to build an SoC. How shall we use the interconnect to work with other existing system IPs that were provided by other vendors in ARM camp, for example?
Oh, this one's real easy. There are open source implementations of Tilelink converters to APB, AHV, AXI. So if you want to do this, you can just wrap up those IPs with a converter and then attach it to the Tilelink network. We do that with all sorts of IP that we acquire when we build an actual chip.
And also for OmniXtend, that's an open specification. So if someone wants to put it on a processor other than a RISC-V processor, then that's also possible. So it's an open standard. That's one of the key differentiators.
Correct. And I actually know of several startup companies that are using Tilelink in the non-RISC-V chips. So it's already happening. I don't know if they use the open source bus adapters that Wesley mentioned or some other ones, but it's being used. Ted, are you still there?
I'm still here. Yeah, I just figured I'd give everybody another second before we, sort of officially sign off. There's 4 of me?
There's 4 of you, yeah.
Well, the last thing you want is to clone me. I can absolutely assure you of that. Okay, so I think, we have recorded this, so we'll be posting it. And I already sent out the link for the box folder link for everything. So I don't think there's anything else. We can hang here for just a few more seconds to see if anyone has a question. And if not, we can just, wish everyone a good night. Thank everybody for attending.
Thank you, Ted.
Thank you. Thanks, Curt. Thanks, Zvonimir. Thanks, Dan. Thanks, Wesley. Jeffro, really appreciate your help on this as well.
Thank you, everyone.
Cheers.
Okay. Yep. Bye-bye. Have a good night.
Thank you. Bye-bye.
Thanks, Jeffro. Bye-bye.
See you later.
Yep.
Bye-bye. I stay to
stop the recording.
There's still comments coming on a Zoom chat. So
oh, really? Oh, okay.
That's why I'm hanging to